This call is now being recorded. Okay, so now let's get back to the stress tensor. So basically, we know that the stress tensor is basically a tensor which maps the normal vector to a surface with the traction vector at the normal of the surface. So basically, if I have a normal to the surface, then the stress tensors applied on the normal vector would give me the traction vector. The traction vector is basically the force on a surface. And so yes, basically we can see that this is the traction vector, t raised to n dot n cap. So like we can basically again divide it into two components: the Sn component, which is along the normal, and the tau n component, which is just perpendicular to this. So basically, now that we have defined the stress tensor, we have two or three important things to discuss. The one being the force balance, and the other being the moment balance and the energy balance. These three things which we'll be doing for this course. Like now that we have defined the tensor field, and now that we have gotten into the forces after the strain. So basically, let's just start with the force balance. So we're assuming an equilibrium condition. So like we're considering a static case where the force is zero, summation of all force, and summation of all moments is zero, basically. So like considering this as our body, we consider an element P out of this body, which is a differential area ds, and the area is dA, and the traction vector would be acting tau raised to n at that area. So basically we consider the integration overall, and we also define another thing being the body force, as being the body force per unit volume. So like the body force is basically something which acts like on the whole of the body, not just on the surface. For example, gravity acts on like volume. It's a volumetric property. It does not act on a surface, it acts on a infinitesimal volume too. So like F would denote the body force. So for the force balance, now that we have we can write the total force on the body is basically the sum of all the traction forces and sum of all the volume forces. So now that we have this traction, we can try traction as the stress tensors time the normal direction, and this is n dot ds, and this is basically the volume integral. And we can also write this is basically stress is obviously, since it's a surface phenomena, it's on the surface, and this is the stress tensor times the normal vector. So basically we can write apply the Gauss divergence theorem. Since this normal dot ds and this is over the surface, we can convert this into a volume integral. So like to convert it into the volume integral, we have this sigma tensor. So like we apply the divergence of this sigma tensor to convert it into a volume integral. So like now we have both of them as a volume integral overall. So now that we have, we can like basically write about the different types of Gauss theorem. So like if we have a vector, then like for the vector we have the Gauss divergence theorem as the divergence of the vector time in the volume integral. And like for a tensor, we have the divergence of the tensor in the volume integral from the area integral. So like the n cap ds converts into the dv volume, which is right here. So like let's get back to it. So basically we again have this thing where we write the divergence of sigma plus the body force and so over the entire volume of P. So now obviously, since P is an arbitrary volume, so like we can apply the localization theorem, which basically states that if P is an arbitrary volume, we can like consider P to be very small, and we can consider it to be a pointwise for at a point, P to be at a point. So basically for each point this condition should be satisfied, that is the divergence of the stress tensor plus the body forces should be equals to zero. This is basically the mass conservation equation, or sorry, the force balance condition. And after this we have the moment balance. The moment balance derivation is quite involved, but basically we can consider an x vector for this. So like we can consider any origin, and we can consider an x vector where the traction is being applied. So basically obviously the moment would be x vector times the traction vector, and the force would be x vector times the force vector. So basically after a kind of a lot of derivation, it basically like the derivation is not important. It's like only the final result would be important. So basically the final result from the moment balance, we basically have this epsilon ijk sigma kj over the entire volume 0. So it will result to be this identity epsilon ijk sigma kj equals to 0, but which is just basically implies that all sigma should be symmetric. The stress tensor should be a symmetric tensor, and that is basically the condition which we get. So like sigma 32 is equal to sigma 23, sigma 12 is equal to sigma 21, and so like all these are the three conditions that should be conserved if like the angular momentum is conserved, or like the moment is conserved, angular momentum, or the moments are balanced. So that is the condition. So like sigma should be symmetric for a point for at each point to for this pointwise condition to hold. So like after this we have the derivation on polar coordinates, and like which I guess it's not the derivations are not important for this course. Like you can just go through that in the notes, but like we'll just like skip to the final result, and like the final result is right here. So let's just have a recap. So like what we learned is like the force balance leads to the divergence of sigma plus the force equals to 0, and the moment balance leads to that it should be symmetric. The like stress tensor should be sigma should be symmetric. So like sigma transpose is equal to sigma, and like there's this contraction tensor in tensor notation or direct notation, that a contraction b is basically the product wise sum of a and b. Like for each a11 should be multiplied by b11, and it's just like the sum. So like it's a product of two matrices, but like in a element wise manner. And like this is also a trace of I, trace of a, it's aii. And finally like for the for the radial coordinates, like the derivation is not as such important, but like do remember that like we have this, right? We have gradient of sigma plus f is equals to 0, right? So like now this gradient divergence of this stress tensor can be written in radial coordinates as this form. So like this is the divergence of sigma, r component of the divergence of sigma vector, and this is the theta component. So like you can basically derive that. The derivation is in the notes, but like you can basically just memorize these formulas for the components, or the like curvilinear coordinates. These are the components uh, for the for the divergence of the stress tensor, like this divergence of sigma basically. So like with that we conclude the force and moment balance and the radial coordinates, and I'll see you in the next video.